Okay, welcome back to the second half of chapter 23. We're going to look at some of these other reactions that we have in the balance of the chapter that are related to the ones we just talked about. And what I'd like to discuss with you now are the intramolecular aldol reactions. The ones that you were looking at were intermolecular, between two separate molecules. These are intramolecular, within the same molecule. Now this reaction applies to dicarbonyl compounds, species with two carbonyls obviously. And normally it's used to form 5- and 6-membered rings, okay, because those rings are pretty stable. They don't have a lot of strain in them. Occasionally you'll see 7, and sometimes even other numbers, but let's pretty much restrict it to 5, 6, and occasionally 7-membered rings, because they don't have a lot of strain. Now, one thing we want to discuss before we get too far ahead of ourselves is that the dicarbonyl compound, you really want them to be symmetrical. Okay? In other words, look at 2,5-hexane dione. Okay? 2,5-hexane dione. Is this molecule symmetrical? Do you see a line of symmetry anywhere where one half is equal to the other half? You do. Okay, and that line of symmetry would be right here. Okay, let me just sketch that. So if you think back to NMR, if you're asked how many carbon resonance lines would this one display, it'd be 1, 2, 3. So there's a symmetry axis here in this molecule, all right? And you do really want your dicarbonyl species, you really want them to be symmetrical, okay? If they're not, you're going to get a mixture of products. So what I'd like to impress upon you is the chemistry here is no different than the chemistry that we had throughout this chapter. You say, what do you mean by that? We're going to join an alpha carbon to a carbonyl carbon, okay, to make an aldol, and then we're going to do an elimination of water to make an enol. So to really grasp that, we kind of have to re-sketch this. But just again, think of it this way. This is an alpha carbon, right? And it's the same as that one. So let me just put an alpha here. Now these are alpha carbons also, okay? But they can't join the carbonyls because that would be too small of a ring. So in this case, we're going to join an alpha carbon to a carbonyl carbon. Or it could be that one joined into this one. Either way. But the rules are the same. Now, let me try to impress upon you one more thing. Let's figure out how big this ring is before we actually do the product. I'm going to start at this alpha. 1, 2, 3, 4, 5. And I'm going to number over to the carbonyl, the second carbonyl. 1, 2, 3, 4, 5. If you do that, that's going to tell you how big your ring is. What did we say, 5? So that's why you're going to get a 5-membered ring, because you're joining the alpha carbon to the second carbonyl. 1, 2, 3, 4, 5. So if this were an ethyl group, right, you would still start at the alpha carbon. If this were propyl, always start at the alpha carbon on one end, go through the one carbonyl to the second carbonyl, counting them. So in this case, 1, 2, 3, 4, 5, and it tells you how big your ring is going to be. It's going to be a 5-membered ring. Now, to figure out how it works, okay, intramolecularly, in the lab setting, you would have this very dilute. Okay, you'd have a whole lot of ethyl alcohol there, because you don't want it to react intermolecular, it would be intramolecular. So you have this molecule very much spread out. So what I've done is I've taken 2,5-hexane dione and I've redrawn it, right? So that you can see this a little more closely. So here's my alpha carbon that I would explicitly show on the hydrogens. And the base that we're using here is a strong base. It's a phthioxide anion. Let me just sketch that. This is the one that y'all used back in the malonic ester synthesis and the acetoacetic ester synthesis. There's a phthioxide anion. And as you know, there's 3 lone pairs. They kind of run out of space for one of the lone pairs, but there's 3 lone pairs. any one of those lone pairs, okay, will pick up a proton from the alpha carbon. Okay? Alright, so we're just showing something you've seen all along, deprotonation. And by virtue of doing that, you produce the conjugate acid ethyl alcohol. Okay? But more importantly, you've generated an enolate. Now I indicated that this is very dilute. Okay? This could attack another molecule of that, but if it's very dilute, you can do an intramolecular reaction. Okay? You go right there, intramolecularly, and form a carbon-carbon single bond. And what do we get? We get this alkoxide intermediate. Okay? This alkoxide intermediate. Now bear in mind that we have ethanol here. Ethanol is going to function in this case as a Bronsted acid. It'll donate a proton to that alkoxide anion. So what do we get? Here's our aldol. So this is an aldol intermediate, so to speak. And let's just remind ourselves that our new bond was formed right there, and I'm going to highlight it in yellow. There's your new bond. Carbon-carbon bond. And yes, this is an aldol. Now, what do we know about aldols? They're prone to what? Dehydration. Well, how do they do that? You got to have a base around, don't you? So we have ethoxide anion that we've been speaking about. Here it is. And these protons, okay, are mildly acidic. But we have a good driving force here, and that is the conjugation of this species. Those pair of electrons will collapse, and here the world's worst leaving group will leave. But it falls into conjugation. Okay, so that's why the driving force is favored towards this. And what is this known as? This is an enone. Only now it's in the form of a ring. So the chemistry is the same. There's no difference in the chemistry. It's just now we're doing it intramolecular. Let's try another one. Okay. And this one's pretty interesting. It says what product would be obtained from base treatment of 1,6-cyclodecane diol. In other words, that's 1,6-dichlorine. You don't even need to know the name here, okay? But you can look at it. Now, the first question I have for you, is this symmetrical? So did we say we wanted to be symmetrical? And the answer is it is. So you could draw a line here, right through there, and you could go that way. You can see, yes, it's quite symmetrical. Carbon-13 NMR will give only 3 resonances. So we have 4 equivalent alpha hydrogens. And what do we want to do? Well, if you look back on the previous problem, what did we do? What we did was we joined an alpha carbon. And I'm indiscriminately choosing that one. Don't choose this one or this one, it doesn't matter. We're going to join that alpha carbon to a carbonyl carbon, right? Yeah. So you can see at a glance. So we're going to close this up, and we're going to end up having 2 rings that are fused. Well, let's think about the size of the rings, okay? Now I'm going to put a green dot here, and I'm going to number all the way around to there, okay? So 1, 2, 3, 4, 5. We're going to have a 5-membered ring on this side. What about the other side? So let me just put a 5 in here prematurely, okay? In other words, if you connect that to that, that's a 5-membered ring. What about the other side? 1, 2, 3, 4, 5, 6, 7. So we're going to have a 7-membered ring and a 5-membered ring, okay? They're going to share these 2 carbons. So that might be a good place to start. So let me go ahead and draw a 7-membered ring. There's a 7-membered ring. Okay. And here, let me draw a 5-membered ring. Okay. So if you've gotten that far, you've come pretty far, all right? All right. So I'm going to draw this as our aldyl intermediate first, okay? And here's where that carbonyl would be. All right, and there's your OH. So this would be your aldol, all right? Let me put in square brackets, okay? This is your aldol intermediate. And it has all the same features that all the other aldols would have. Let me put a hydrogen there just so we can make the case. And like I said, here was a 7-member ring, and over here we have a 5-member ring. Okay? Now you've got a strong base in sodium methoxide. So if we could lose this proton, okay, form a double bond here and eliminate that OH, we would be conjugated and end up with a more stable species. And that's exactly what's going to happen. It's going to conjugate into an enone. So let's get the enone on this side. Alrighty. Double bond there, and if you want to put water over here, you can. So here's our aldol, and our aldol form our enone. So again, this is intramolecular aldol condensation to form an enone. Now, just as many times you're asked, well, how do you make that? I need to make that. How do I make it? Well, if you can spot where you have a carbon-carbon double bond, right, then you pretty much have it made. So I'm going to draw that whole structure minus that double bond. Right? Make it kind of big, and you'll see why in a moment. Now, the answer I'm giving you isn't exactly the way I would draw it, but it's okay, because I'm trying to make a point here. Alright. Okay, so you rip that out, and now what do you have to do? You got to fill in just like before. This is going to be carbonyl. This is the methyl. These have to be symmetrical, so this is the methyl also. So this is the methyl showing all the bonds. This is just a methyl showing it as a CH3. So this is fine. You can just leave it like that. Now if you're a zigzag type of person, we can do that as well. Let's just count the carbons. 1, 2, 3, 4, 5, 6, 7 carbons. Alright. And put carbonyls on the ends. Right. And I'm going to dress it up a little bit. We can put that there like that. You know, 1, 2, 3 methylene. Well, yep, that's it. Okay, so these are the same. Right. So either way you want to draw it, that's fine with me. You can see though we have a symmetrical dicarbonyl or diketone. So this is how you could make that particular enone product. Now, we're getting near the end of this chapter, and I want to describe for you something called the Claisen condensation reaction. Y'all may remember the Claisen rearrangement back when we were in chapter 18. Here, we're the same Claisen, same guy, only it's a different reaction. So let's read what I have here first. This is the base catalyzed condensation between no aldehydes, no ketone, but between two ester molecules, okay? Referred to as the Claisen condensation. Alright, now here's ethyl acetoacetate. That's the one that you used in the acetoacetic ester synthesis back in chapter 19. You say, well, how do we make that stuff? Well, back then you just had it, okay? Somebody had to make it. Well, how did they do it? Using this kind of chemistry. So you shouldn't be surprised that when you see a 2, that always means that this thing is going to react with itself. It is. But it's a little bit different than we had with aldehydes and ketones. Okay? And one of the differences is that we're not going to form enones, okay? We don't do that, and you'll see why in a moment. We're going to stop at the carbon-carbon bond. We end up with 2 carbonyls, not an OH, okay, but 2 carbonyls. So let me give you a simple approach to doing this. And I would kind of like you not just to look at the product, but kind of look over at the byproduct. Because the byproduct gives us, in many cases, a lot of clues as to what's going on. So let me show you what's going on. In the first step, you have to add base, and we know what that's for. That's going to make this into an etylate. Okay, this is going to become CH2, become etylate, and then it's going to react with a separate molecule by attacking the carbonyl. It will. Let me kind of show you that in one fell swoop, and here's how I want to do that. Let's sketch this molecule you see here on the left like this. So far so good. There's my acetyl group. Let me point this part down, okay, just for representative reasons. Okay, same molecule, there it is, same one. And now, okay, they're identical. Now let me go over here and redraw that same structure again. Okay. Say, oh wow, big deal, you do the structure twice, only it looks a little different. No big deal, right? Yeah, this will help you understand what's going on. Folks, what did we say happens when you treat this with base? One of the methyl groups is we're going to become what? That. So we're going to become an etylate. So let me just turn that into an etylate. Can you see what's happening now? Yeah, this is going to act as a nucleophile. Okay? Going to join this carbon to that carbon. And you can probably see right here, there's that new bond. Okay, let me just point that out. That's the new bond. Now this is not SN2, it isn't. Okay, it's not SN2. It sure looks like SN2, but it's not. What happens, and I'll show you this on the next page, this pair of electrons, okay, resides under the oxygen, then it collapses, and then this group is eliminated, okay? And then we'll see later why we have to quench it with acid. So, but this is a quick and easy way, right, to figure out what the structure of your Claisen product is going to be. All right? So these are called beta ketoesters. And that part that ultimately was the leaving group, once you quench it with acid, becomes the ethanol. Right? But the reason you did this reaction was to make this compound. Right? This is why you did the reaction, to make this compound. That just happens to be your byproduct. Okay, let's flip over to page 182. Because I'd like to show you how this mechanism works by looking at that same reaction that we just saw on page 182. So let's complete the mechanism above, mechanism for the above Claisen condensation reaction. Be sure, okay, there we go. Be sure to indicate the utility of acid in step 2. So here's the same reaction that we saw on page 182. And what I've done here is shown you all the intermediates and everything, charges, whatnot, minus the curved arrows for how this process works. So we just have to fill in the curved arrows. As before, you want to label alpha. We recognize that these protons are not very acidic. This is a strong base. So the very first step is simply deprotonation. Okay? You lose a proton from an alpha carbon of the methyl group of ethyl acetate. And what does that give you? That gives you an enolate. Okay? And here's your conjugate acid. Now this was the first molecule, or first equivalent, or first mole, however you want to think of it. So this is our first enolate. Now here's your second. Okay, here's your second molecule of ethyl acetate. So what's going to happen? This is going to behave as a nucleophile to that carbonyl. Okay, it's going to join this carbon to that carbon with a single bond, and then this pair of electrons, okay, will reside on oxygen as a lone pair. So we get this alkoxide intermediate. Now, this is called a tetrahedral intermediate. And the reason it's called that is because where you formed your new bond, right, where you formed the new bond, which was right here, that carbon, which was formerly sp2, is now sp3. Henceforth, it's tetrahedral in geometry about this carbon. So it's a tetrahedral intermediate. Now the next step's pretty simple. Okay, you can revert back, but another thing that can happen is this can collapse, displacing this ethoxide anion, which happens to be the base that you catalyze this reaction with. And so there we have our product. If you look at this structure here, it's identical to that structure there. These are identical compounds. Well, we're done. Hold on, we're not. What happened? We eliminated ethoxide, right? And what do you know about it? It's a strong base. Okay? And look here. What do you notice about these protons? They're between two carbonyls. So the pK is about 13, something like that. So what will happen? That base, if it can't help itself, will pick up the proton from that alpha carbon. So you end up forming this, which is an enolate. Now, we can't isolate that. We need a covalent species. So now do you see why in step 2? Why in step 2 we had to quench it with acid? Folks, the acid will put the proton back on that carbon. And so here is your final product after you quench it with acid. So one thing about the Claisen reaction is you always have to quench them with acids. That's what it's for, just like you'll see in the next problem. So here it says provide the major product of the following Claisen condensation reaction. I think we can do that. Let me work through that kind of like I did on page 182. All right? And what I did there was the following. I'm going to use this space below to work it out that way. So let's go ahead and sketch ethyl propanolate, just like you see it there. And I'm going to go ahead and point this part down. You may be way ahead of me already. So I've just redrawn the same structure, only now I know that I'm going to lose that. Okay. Okay. Now let me draw ethyl propanolate again. This time I'm explicitly going to show that alpha carbon there. Okay. So these are identical. That one, that was all identical. Just they look a little different because the way we oriented the bonds on the page. Well, what's this going to do? This is going to remove a proton from an alpha carbon, right? So this is going to become negatively charged. So let me put an X through one of these hydrogens, right? So one of those is gone. One of those is gone. So from the what carbon? The alpha carbon. And what they're going to do, it's going to go here. This is going to go up like that, form a tetrahedral intermediate, then it's going to collapse back, and ultimately this is going to break off. Again, not SN2. It's not an SN2 reaction. Okay, it involves a tetrahedral intermediate. But you can see all the elements coming together appropriately. So let's just draw, if you can kind of make sense of all this mess, what's going on here. So in effect, the left-hand side of this molecule all stays intact, right? And I'm going to switch colors here. So here's a CH, here's a CH3 like that. And there's your carbonyl over here, and barely squeeze it in there, but there it is. Right? So that's what you get when you do a Claisen reaction on epopropanoate. Right? So give that a try on your own, see if you can come up with the same answer I can. Just cover it up, cover everything up. But if you go through that process, you'll get these right every time. Now, you may remember we did a mixed aldol. Is it possible, you ask, to do a mixed Claisen? Well, the rules are pretty much the same. You can do a mixed Claisen, excuse me, there's something underneath there. Mixed Claisen, but a certain set of criteria has to exist. It's effective if only one ester has no alpha hydrogens. Okay, that's kind of like with the mixed aldol. Now, either the donor or acceptor may be an ester, or both can be esters, and we'll see examples of that. So here's a couple examples I have of how this would work. Both the donor and the acceptor are esters. So let's look at these and try to figure out what's going on. All right, first off, why is this molecule here the donor? Why is that the donor? Because its alpha carbon, right, has hydrogens. So it can become an enolate. And therefore, it can become a donor. It can tack there. This is ethyl benzoate, which is the acceptor. What do you know about it? Does it have any alpha hydrogens? No, it doesn't. So let's write that in. No alpha H's. Okay? This one does have alpha H's. Yes, alpha H's. Okay? So that's the criteria we need. But they're both esters. They are. So what's going to happen, we're going to treat this with sodium hydride. Now before, you've seen things like sodium hydroxide. You've seen sodium ethoxide. Sodium hydride is really superior. Right? Because it's going to generate hydrogen, and therefore there's no equilibrium back towards the product side. It's going to go entirely to the enolate. So just to give you a feel for how that works, let me just make a little side sketch over here. I don't want to go too far with it, but let me just sketch this to show you how that would work and why sodium hydride is really good for doing this. All right, let me explicitly draw all three of those hydrogens on here. Now, sodium hydride is really hard to work with. Okay, they store it in like a mineral oil, and so it's kind of hard to get it out of that. But you can do it. It just takes time. I've done it. But sodium hydride, suffice it to say, is a source of what? Hydride, right? Now, but in this case, it's not a reducing agent, okay? Instead, it's a Lewis base. So sodium hydride is a really strong base. So what will it do? Just what you expect it to. It'll pick up a proton from an alpha carbon. And when it does that, right? When it does that, you eliminate hydrogen gas. It's going to leave, it's going to depart. So there's no back and forth equilibrium there. There's no back and forth equilibrium at all. Instead, you're going to end up with pure enolate. Now, they typically don't do this in an industrial setting because the hydrogen is extremely flammable. So that's why we would do that, right? And sodium is just a spectator ion. This is your enolate. And it's what's going to be the nucleophilic component. So suffice it to say, let's just change this to a 2. All right, put a pair of electrons on there and a negative charge. Let's draw a curved arrow there. And we remember it's not an SN2, it's not. But we're going to show it kind of like it was. We're going to form a bond between here and there. There's your product. So this works the same way as the Claisen reactions on the previous pages. It does, only now it's mixed because you have two different esters. And you know why that acid's there, right? That acid was there to quench this reaction. because a little bit of enolate could still be around, but you're going to put a proton back on. Okay, let's keep going. The donor and ketone and acceptor is an ester. Okay, so it's still considered a Claisen because at least one of them is an ester. All right, so here we have our alpha carbon, right? And you know that when you do this reaction, you're going to take one of those off. Let me just draw it kind of like this. I'll just draw a portion of that molecule. I won't draw the whole thing. So 2,2-dimethylcyclohexanone is going to become an enolate. And what will it do? Intact with carbonyl. Now folks, there's some bad leaving groups in the world. This has like the 2 worst leaving groups. Hydrides are terrible. Ethoxide's terrible. But ethoxide actually is less terrible than hydride, so it'll break off. The conditions are extremely basic, right? So yeah, that's what would go on here. So this would be a mixed Claisen reaction. And again, you add acid to put that proton back on. And so the reason we're doing this reaction is to generate this product. Okay? Now let's see if we can do one of these two. Why is this a mixed Claisen? Well, because this is an ester, that's an ester. Only one of them needs to be an ester, but they're both esters. But what is it about it that makes it mixed? These esters are different. Okay? This one has no alpha hydrogens. And this one has, yes, it has alpha hydrogens. So this will be the donor, this will be the acceptor. Okay? Alright, so you know that we're going to lose one of these 2 hydrogens, right? Okay, this will end up being negatively charged. So we'll have a carbon here, and I'm just going to draw an arrow. Remember that proton's gone. It's going to go in here, okay, I'm going to break that off. It's just a quick and easy way to do this. And over here we can predict our product pretty darn quickly. So remember, when you break a group off, you're always breaking off, okay? In every case, you're breaking off an oxygen alkyl component. You're eliminating those from the tetrahedral intermediate. All right, so, and we're going to make a dicarbonyl species. So here we have a methyl, and here we have a hydrogen. Now you may notice this carbon's chiral, right? So, but you get, it's racemic. That's FYI, you get a racemic mixture. 50% R, 50% S. So alpha, okay, alpha would be 0 degrees. And what that did, alpha is 0 to no. Optically inactive. And the byproduct here, of course, will be methanol. For what it's worth, okay, methanol, because we broke off a methoxy group. So these are examples of a mixed Claisen. And just like you have intramolecular aldehys, we have intramolecular Claisens. And the person who came up with that, chemist named Dieckmann, called the Dieckmann cyclization. So it's applicable to diesters, and normally used to form 5 and 6 membered rings. Can you form 7? Probably, but not 4, and too much strain there. But it works pretty much the same way. So here's an example. Okay. Let's take a look at this. Now, as before, you want these esters to be symmetrical. You don't want an unsymmetrical ester. So this is a symmetrical diester. We should really call it a diester. So what's going to happen? What you need to do is locate an alpha carbon. There's an alpha. and there's an alpha. Now, kind of set it up where we're going to be focused on that. So, this alpha carbon is going to become an enolate, and intramolecularly it's going to go right there and form a bond. And as you've seen before, this is going to break off. Right? So, let's count the carbons going from alpha. 1, 2, 3, 4, 5. Yeah, 5-membered ring. And you can see that over here. So the new bond, okay, the new bond was actually right there. Okay, that was the new bond that you formed when you did the intramolecular. Now what I've done, I've left some space here. See if you can do the mechanism. Right? See if you can do the entire mechanism going from here to there in this space. Okay, and I have it worked out more in the notes that I've placed on Canvas. You can see that yourself. That'd be good practice for you. Okay, we're just about done, guys. Let's go to section 2310, where we have conjugated carbonyl additions, the Michael reaction. All right, this is named after R.B. Michael, and this is really good. This is really good chemistry. Folks, this involves nucleophilic attack of an enolate, and you know what those are, to alpha-beta saturated ketones, aldehydes, or nitro compounds, even amides or nitriles. So, very versatile reaction, super powerful reaction. So what we're going to see here is that an enolate, and this is something we said at the very beginning, okay, enolates can act as nucleophiles. So we're going to call it a Michael donor, okay, because it's nucleophilic. And the alpha-beta unsaturated species is going to be considered the Michael acceptor because it's electrophilic. And that the alpha-beta species, okay, that we talked about here, they're also called what? Enones, irrespective of whether they come from ketones or aldehydes. So here's the general reaction, okay? We got to remember, folks, that the carbon here, the beta carbon, is delta plus, right? It's delta plus. So, and over here, if we draw a resonance form of that, we would have the oxygen, of course, being delta minus. So nucleophiles, in many cases, will attack there. Now, as you know, Grignards won't; they'll attack here. So this is conjugate addition. And we call it conjugate addition because this is the conjugated species, the little green tick mark, conjugate addition. So in the whole overall process, we formed a new bond. We really built this molecule. And then after we quench it, we end up with the neutral species over here. Now this may look really complicated. In some sense it is, but you're going to see some really general patterns here in the very last page, 186, as we go. So let me show you a specific example, and then I'm going to show you a more detailed example for how you would do this. All right. We spend a little time here. Folks, this is ethyl acetoacetate. Okay, you would get that from a Claisen reaction. And we also call that acetoacetic ester. It's going to be your what? It's going to be your donor molecule. In this case, it's going to be a Michael donor. And the reason, because they have alpha hydrogens. There's two of them. And the pK there, okay, it's about 12, so on and so forth. So that base can remove one of these protons. Now this is your acceptor, or in this case a Michael acceptor. And you can spot those because they have a double bond between alpha and beta. Okay? Now, two separate compounds. You're going to add base. What's the base going to do? The base is going to take that proton off, right? And so this is going to become an enolate. And what's that enolate going to do? It's not going to attack here. It's going to attack the more electropositive carbon. It's going to attack there. So we're going to form a bond between this carbon of the enolate and the beta carbon is the acceptor. Right? And then, much like the ordinary Claisen reaction, we quench it with acid. And that's all we're doing here, guys, just enough to get the pH around 7. And if you look at all that together and how all this came about, okay, you can see that this is our new bond. Let me highlight that. That's your new bond. Your new carbon-carbon single bond. So you built this molecule up. So this has a name. It's called the microproduct. In chemistry, we often call this the conjugate addition product. And you can always spot them. See, I can always spot them. Guys, always look for 2 methylenes, okay, next to a carbonyl, and you know it came from a Michael reaction. Okay? So we'll do one of those here in a moment. But let me just give you an overall feel for how this works. Here's some specific Michael acceptors. What do you notice they all have in common? Is there anything they have in common? Can you tell anything common about all of the 1, 2, 3, 4, 5, 6 different compounds? I'm going to draw a line here and ask you that question again. Is there something they all have in common? And the answer is yes, I see it. They all have an alpha-beta unit of unsaturation. And they all have what? An electron withdrawing group on them. Yeah. So this is an aldehyde, this is an ethyl ester, this is a nitrile, this is a ketone, nitro, and this is an amide group. These are all electron withdrawing groups, which means that for every one of these, this carbon is delta plus, which means nucleophiles want to form bonds there. So that's what all the Michael acceptors have in common. What about the Michael donors? What do they have in common? Many of them are dicarbonyl species, but not all of them. Okay? But they all have acidic protons. These are the ones I highlighted in kind of a, not highlighted, but in bolder font, with at least one electron withdrawing group on it. So these are kind of more general. So this is an acetoacetate between 2 carbonyls, right? That means the proton's acidic. So all of these protons in bold font are acidic. Therefore, they can become enolates. So all can form what? Enolates. Enolates. If they can form enolates, that means they can be nucleophiles and they can attack these. All right. Okay, so beta diketones, beta ketoesters, malonic ester, beta keto nitriles, all of these can form enolates. All right. All right. So, what's our job in organic chemistry? What do we always want to do? We want to know how to make stuff. So, how can the following compound be synthesized using a Michael reaction? In other words, give the structure of the Michael donor and acceptor molecules. I clued you in a little while ago when I told you to look for 2 methylenes. Right? You see them? That's a giveaway, guys. That is a giveaway. That tells you where you need to break this molecule apart. It's always right there. Okay, because this is going to be your alpha and this is going to be your beta carbon. Right? So let me highlight that whole thing. So now we're ready to draw instantly our Michael acceptor. So let's sketch it. Let me sketch it this way, because we don't want to get too far ahead of ourselves. So there's the backbone, but this is going to be your what? Your Michael acceptor, because it's got electron withdrawing group. But what do they all have in common? Double bond, right? And an alpha beta unit unsaturation, alpha beta unsaturation. So this simple compound, nitroethylene, is your Michael acceptor. Now the rest of the molecule that you see over here, everything to the left of my finger, that's going to be the microdonor. Let's take a look at that. So, knowing a little bit of organic chemistry and kind of seeing how these things come together makes seemingly difficult problems become pretty easy. So I'm going to draw everything that I see there, maybe a little bit more. That would do it, but let me go ahead and sketch in the hydrogen. Okay. So that would be the molecule that's going to result in a donor. Because here's the carbonyl, there's the carbonyl part of an ester, so this proton is acidic. Therefore, that base can remove it. This can act as a nucleophile there, forming that new bond. Okay? All right. Now, we're done, but I did want to add just one more little feature here. I said, no, we're done. Stop, stop. Folks, this is just a quench. All right. In other words, all you're doing there, all right, is to put a proton, right there on that alpha carbon. Okay, you're not doing anything beyond that. But if you were to take it a little further, you can move that like this, and you added more acid, okay, and you heated it, y'all know what would happen? Think back to the acetoacetic ester synthesis and the malonic ester synthesis. You would hydrolyze that, okay, that ethyl ester from the acid, and the heat would promote that, and then it'd undergo decarboxylation. So actually, if we went one step further, this is what the product would look like. Decarboxylate there. And that becomes the hydrogen. Okay, and that would be your product. And of course, you produce ethyl alcohol, right? And you produce CO2, right? But I just wanted you to keep in mind that some of the chemistry we learned back in chapter 19 fits very nicely here as well. Okay. Okay, guys, believe it or not, we're done. We are done. See you later.